Welcome to In 5 Minutes. The agenda of this clip is to identify VOH and VOL for a resistive load inverter. We have already studied the basics of resistive load inverter in the previous clip, and we have identified that in order to find the critical voltages, we need to equate the currents IR flowing to the resistor and current ID flowing through my NMOS transistor. Okay, let's get started. VOH, we know that output is high. Because it's an inverter and the output is high, we can easily say that input is low. So now what we need to identify is what value of ID to take, whether the NMOS transistor is in cutoff region, linear region, or in saturation region. In order to do that, let's see if input is low. Input is nothing but VGS. So we can easily say that VGS is low. Low means nearly equal to 0. So let's start. VGS, which is nothing but Vin, is approximately equal to 0, will surely be less than threshold voltage VTN, which is 0.6 to 0.7. This easily says that my transistor is in the cutoff region, and the cutoff region, my value of current is equal to 0. Now let's equate the two currents, IR equal to ID. IR is nothing but the current flowing to the resistor, which is nothing but difference in the voltages, VDD minus Vout upon the load resistance RL, and ID is 0. This is nothing but VDD equal to Vout. As we are finding VOH, my Vout is nothing but VOH. So this gives me a value of VOH equal to VDD. So for my resistive load inverter, my value of VOH is equal to VDD. Now let's go ahead and find the value of VOL. We'll follow the same methodology. For VOL2, by definition we know that output is low. Output low means input high. Input high equal to VDD almost. Let's identify the region of operation for my NMOS transistor if input is high and output is low. So input high equal to VDD, which is, say the value of VDD is 1.8 volts. This will surely be greater than or equal to 0.7 volts, which is nothing but my threshold voltage. So now my transistor is on. The thing which we need to identify is whether my transistor is operating in the linear region or in the saturation region. So for linear and saturation region, this is the equation which differentiates whether the transistor is operating in the linear region or in the saturation region. Let's quickly do that. VDS, let's put a dash, VGS minus VT. Now we know that VDS is nothing but Vout, VGS is nothing but Vin minus VT, threshold voltage. This is also VT, capital T, remember that, because we'll be also studying switching threshold in the other clips which will follow. So we know that output is low, input is high. This we have got it from here. So this says that the sign is going to be less than, and this gives me that my transistor is operating in linear region. So what we need to do next is nothing but equate the values of current in linear region with the value of the current flowing across the resistor RL. ID in linear is equal to IR. Let's write the equation of the current in linear region. We already have it on the screen on the left hand side. Kn by 2 twice VGS minus VT into VDS minus VDS square is equal to VDD minus Vout upon RL. In the next clip, we are going to study the final value of VOL. How do we get it after equating these two equations of current? So stay tuned for the next clip for the actual value of VOL. Thank you. Hope you have enjoyed it. Stay tuned.